Good afternoon, everyone. How are you doing? Are there any questions about lecture in our last class, or the notes, or the slides, or anything like that? So I've been constantly updating these things. The lecture slides, the slide decks have been updated 30 minutes ago, so go grab those, an updated set. Chapter 1 is broken into 2 slide decks. Chapter 2 is as well, so both of those are now up online. And I think we'll probably stick or be stuck in the first slide deck of chapter 2 for this whole lecture. And then we'll get to the next slide deck probably on Tuesday. Right now we're focusing on notation and fundamental ideas, solidifying some of the notions that we talked about in chapter 1. After we get through the main definitions, we'll go back and tie up a few loose ends of some things that we talked about. Not everything, but a couple of the things that we talked about in chapter 1, we're going to put on a firm foundation now that we have definitions and some theory. Last time we ended about in this area. I'm pretty sure that I covered this, the statement of this result. It claims that little o implies big O, and the proof is left to you. But here's the complete statement. Suppose that D is an open set in CD, complex D-dimensional space, that is. Epsilon is a point in R. This is the thing to which epsilon is converging, epsilon naught. Delta is positive, and we assume that f and g are continuous functions from this Cartesian product set into the complex numbers. Suppose that for some x in D, that f of x is little o g of x as epsilon goes to 0, then it follows that f of x is big O of g of x as epsilon goes to epsilon naught. In other words, the short way of saying this is little o implies big O. I think the proof isn't too difficult because remember, we can prove a certain inequality with little o for any alpha. I believe we use the parameter alpha. Well, one of those alphas can serve as your value of C, and therefore you're done.
Yeah, you said prove it like one month.
Yeah, exactly. Yeah, because you the little o definition involves alpha going to 0 for every alpha greater than 0. So really that means alpha getting smaller. So pick one of them and that can serve as your C value. Again, same assumptions about D and epsilon naught and delta. Assume that f and g are continuous functions from the Cartesian product given here into the complex numbers. And suppose that x is some point in D. We're going to assume that g of x epsilon is not equal to 0 on every, or for every epsilon. We're fixing x. And we're going to assume that it's not equal to 0 for every epsilon in this punched out set. So this is going to be the set. That's I delta. Epsilon naught is here. This is epsilon naught minus delta, epsilon naught plus delta. And this set that gets the star, that has that point punched out. Okay, so that's all I mean. So for every epsilon in this interval, it could be over here, could be over here, could be over here, here. Okay, as long as it's not this point, we're not considering that point, then as long as it's somewhere in this interval, g of x epsilon is non-zero, okay, because I don't want to be dividing by 0. Then f of x is big O of g of x as epsilon goes to epsilon naught. And of course, the usual idea here is that epsilon naught is generally going to be 0. If and only if the limit as epsilon goes to epsilon naught of f of x over g of x is 0. Okay? So we've got to prove two directions. If and only if IFF, by the way, that's my abbreviation for that, means if and only if means it's implied and it implies and is implied by. So usually when we have a mathematical statement, we'll represent it by A. Another mathematical statement represented by B. If and only if means that A implies B and B implies A. And we abbreviate this by saying that A is implied by and implies B, or if and only if. That's my symbol for if and only if. Okay, so the mathematicians in the audience have seen this symbol before, and the scientists and engineers may not have, but I think you understand this concept, and that's the notation I'm using. So I have to prove two directions. One is if I assume this, then I need to prove this. And then the other direction is if I assume this, then I need to prove this. Okay. And this is going to be the most useful form of this little O notation that we're going to have. Okay. In other words, we will forget the definition and mostly use just this. Okay. So suppose that f is little o. I think I may only do one direction here. Let me just check. Yeah. And I claim that the other direction is just a reversal, and I think it mostly is. Suppose that f starts out as little o of g. So we're starting on this side. That's our A statement. We're going to try to show that that implies the statement B. So f is little o of g as epsilon goes to 0. For every alpha, there exists a number delta naught such that, or well, delta naught is between 0 and delta, such that if epsilon is in I delta naught epsilon naught, then f of x is less than alpha times g of x in absolute value both sides. Make sense? That's the definition. So we want to show that that somehow implies this statement here. Now, I can divide both sides by g of x because it's not going to be 0 at any point except for possibly whenever epsilon is equal to epsilon naught. And so I'm going to exclude epsilon naught because that's kind of a trivial place anyway. Epsilon equals epsilon naught that's the limit point. So I can exclude that. So it follows, then I can divide both sides by that function g, in fact, the absolute value of that function g. And when I do that, I just get this. Now, you might say there's a bit extra added in there, but it's really 0. It's nothing because I'm subtracting 0. So if I want to show that this quotient has this limit 0, what do I have to show? I have to show for every alpha, there exists a delta such that this minus this is less than alpha. That's the mathematical epsilon delta proof that a limit is, or a function has a limit that you claim it has. Typically, you'll see it as that thing will be the L. Okay, so in case you've never seen it before, let's write it out, right? Well, let me finish it and then I'll write it out for you. If you've never seen the epsilon delta definition of limit. So they used in the United States, they used to teach in calculus the epsilon delta definition of limit. So for those of you who remember, how many of you saw the epsilon and grew up in the United States? Not all of you have. How many of you grew up in the US in your calculus class, you saw the epsilon delta definition of limit? Okay, so it's, fewer and fewer calculus courses are keeping that. Whenever I saw it for the first time, it blew my mind. Okay. Some of you raised your hand in the chat. When I saw it for the first time, it blew my mind because it was just so different. But it's really the basis of the calculus, okay, or of calculus. In any case, we'll get to that in a second. So this is really, by definition, the meaning that this quotient has this limit as epsilon goes to 0. So the only way I can really convince you of that is by writing down the epsilon delta limit. Okay, now I'm putting myself a bit on the spot here, so I have to make sure I get it right. And so you guys will have to check my definition. So f of x, or I should say limit as, I'm going to use x, goes to x naught, f of x is equal to L if and only if for every epsilon greater than 0, there exists a delta greater than 0. Delta in general is a function of your limit point, right? And yeah. Such that if x is any point in the interval x naught minus delta, x naught plus delta, but not equal to x naught itself, then f of x minus L is less than or equal to, or you can replace it with less than, epsilon. Does that look right to everyone? What's that? Oh, yeah. You're good. You're right. It always depends on epsilon. Well, generally speaking. Okay, so if I can find, for every epsilon, I can find that delta. And if x is in this interval, then that has to be satisfied for me to be able to say that I have a limit. So now up above, I'm not using epsilon, I'm using alpha. I am using delta. I think, well, actually delta naught. So I've switched around the definitions here or there, or the notations here or there, but that's basically what I'm doing. Let's go to another example. So now that we have this cool little tool for proving that two functions are little o of each other, I can use that to do some examples in a fairly slick sort of way. Suppose that p is greater than 0, then I think this one we have to be very careful, remember, because I made some mistakes involving reciprocals and negative signs before. I think this is okay. E to the minus 1 over epsilon is little o of epsilon to the p for any p. Oh, wow, I'm missing a p. Not sure where that went.
I don't think you need that because you always supposed p greater than 0.
True, that's a good point.
So that should be a full stop.
Yeah, let's just make it a full stop. Okay, so let's examine this. Epsilon is going to 0, so 1 over epsilon is getting large. So minus e to the minus 1 over epsilon is getting really small. How small? Exponentially small. And that should be less than, right, any epsilon to any power that you pick. Okay, so I think we've got it right. So now we just have to do the calculation. So what is the calculation? If I'm really to show this, I have to prove that, so this is my G, this is my F. I have to prove that the quotient F over G limit as epsilon goes to 0 is equal to 0. So I forgot to write that. So that's what I aim to show. Okay, so it follows from a previous corollary that, and well, let's make sure it does, that e to the minus 1 over epsilon is less than e to the p, right? So this we did show. Well, more or less. We showed it for whenever you have a large parameter. So what was the thing that we showed? We showed that for that large parameter case, it was e to the minus lambda is less than 1 over lambda to the p. Okay, right? So just replace epsilon with 1 over lambda and you have your result. Okay, so we have that. So, well, let's say we have it once we make the replacement epsilon or lambda equals 1 over epsilon or vice versa. They're reciprocals of each other. Okay, so for all epsilon greater than some epsilon naught, which depends on p in general. And that's because we argued that the number that lambda has to be greater than, which we called m, depends on p. That's not a good notation though. I don't like that. Epsilon naught, epsilon. Usually that means my limit point. So give that a tilde. That's better. Okay, so, and a similar argument, so we've shown it. So this guy is a lot smaller than this. So that's going to have to tend to 0, right? If you just divide epsilon p on both sides, right? That's going to get squashed down to 0. And a similar argument shows this whenever z is going to infinity, right? Okay, so this is an interesting and useful result that we'll use again and again. E to the minus 1 over epsilon is order epsilon to the p power for any p as epsilon goes to 0, and similarly, statement like this. It comes up so often that we're going to give that a special, functions that have that property come up so often, we're going to give it a special little definition. Suppose that epsilon naught is in R, delta is greater than 0, and f is some function now just from an interval into the complex numbers. Suppose that's continuous. We say that f is a transcendentally small term as epsilon goes to epsilon naught, which is abbreviated as TST. Okay, you'll hear me say TST a lot from this point on. If and only if f is little o of epsilon minus epsilon naught to the r power as epsilon goes to epsilon naught for any r. Okay, so notice that we have exactly this case here. R's playing the role of p. Epsilon naught, of course, is 0. We're going to 0 simply there. But notice that as this guy goes to epsilon naught, epsilon minus epsilon naught is going to 0. So it's basically the same idea. Okay. Did I write that twice? No. Okay. The next one, it looked like it was exactly the same definition, but one is for epsilon getting small, going to a finite limit, and the other one is for lambda getting large. Lambda gets large. We say that f is a transcendentally small term as lambda goes to infinity, abbreviated TST again, if and only if f is a little o of lambda to the minus r. Okay, so I kind of call this polynomially small, right? It's polynomially small, but as lambda is getting large, because it's a reciprocal monomial. Okay, so let's consider this function f of lambda equals e to the minus lambda. Then this function is clearly transcendentally small as lambda goes to positive infinity. And that's because we can say that f of lambda equals little o lambda to the minus r as lambda gets large for any, this is my symbol for any, which I'll use from time to time. It's like some sort of pagan symbol for any r positive. Okay, and that's exactly what I have right here.
The name is quite misleading. I thought it's like at least order e to the negative lambda. But because it says trans.
Oh. Transcendentally small just means that, so yeah, it's basically exponential. The reason it's exponential is because it's polynomially small at every polynomial order.
Oh, yeah.
Right? Because it's polynomially small for every polynomial order. Okay. Now, so we've defined big O notation, little o notation, and the next thing we want to define is something that comes up an awful lot, and that is whenever we say that two functions are asymptotic approximations of each other, or one is an asymptotic approximation of the other, for example. We've already used this in one of the examples that we did in chapter 1, and now we've got to put it on a firm foundation by a definition. Suppose that D is our usual open set, epsilon naught is a point in R, delta is greater than 0, and F and G are continuous functions from that Cartesian product into the complex numbers. We say that G is an asymptotic approximation of F. G is an asymptotic approximation of F, or 2F. As epsilon goes to epsilon naught. And remember, this is, again, this is pointwise in X. So for every fixed X, this has to hold. If there is no X value, then better still, okay? The notation that we're going to use for asymptotic approximation to is F twiddle G. F twiddles G and G twiddles F, okay? Whatever. As epsilon goes to epsilon naught. And here's where the definition comes. The definition always follows the if and only if. Okay. So this is all symbols and words, but what it means in other symbols and words that we have defined previously is that F minus G is little o of G as epsilon goes to epsilon naught. That's the official definition. Now let's use some of the things that we've seen before. Now, roughly speaking, as long as G is not 0, right, except possibly at epsilon equals epsilon naught, then what we can do is let's compute this limit. Compute this limit. Well, what does this limit tell you? Well, we know that G over G is going to be 1, and F over G, well, that's the limit we want to find out. Okay, so that has to be equal to this limit, okay? Or let's say this guy is equal to 0, which, by the way, so why am I setting this equal to 0? Well, that's because F minus G has to be little o of G. And the only way that that can be true as long as G is not equal to 0, blah, blah, blah. If and only if this has limit 0, right? Whatever is over here divided by whatever is here, well, that quotient has to be 0. That's according to what we said here. F, now put something else here, for example, F here and put H here. So F is little o of H if and only if the quotient F over H is 0 in the limit as epsilon goes to epsilon naught. So now I'll have F minus G over here and G here. So I put F minus G here and G down here. So F minus G on top in the numerator, G in the denominator. That limit has to be 0 for this to hold. That's how we just defined F is asymptotic to G. But of course, now I can define, or now I can divide G by G, right? Write this as the difference of two quotients. That's just going to be 1. And so this has limit 0 over here, if and only if this has limit 1 over here. So basically what we're saying is if F is asymptotic to G or G is asymptotic to F, you can read it however you want. F is asymptotic to G, then the limit as epsilon goes to epsilon naught is 1. So basically these guys are pretty similar functions as epsilon goes to epsilon naught. Okay, at least at their point values at X have to agree. Okay, so to use that little trick involving the limits, all you have to do is worry about, or all you have to do is make certain of, is that G is not equal to 0 at epsilon equals epsilon naught. Okay, if you make the same assumption about F, then I can use my little limit trick. And I can prove this little proposition. Suppose that F and G are continuous functions such that F is an asymptotic or is asymptotic to G as epsilon goes to epsilon naught. And if neither of them are equal to 0 in the interval not containing the point epsilon naught, so you punch out that point, as long as they're not 0, I might have said that wrong previously. This is the correct statement. As long as they're not 0 in an interval that doesn't contain epsilon naught, then we can reverse the asymptoticness. So G is asymptotic to F. And the reason is because you can just flip this quotient. You can just flip it and take the other limit. On the one hand, you're assured that you're not dividing by 0 because G is not 0 in the interval. And if you flip it, take the reciprocal, then you're assured that G is, or F is not 0. In either case, you're going to get a limit of 1. All right. So you're covered in both cases. So that's the simple proof of that. Does everyone understand?
That makes it reflexive.
Yeah.
Is it transitive?
I forgot actually. It's possible there's a simple example where that's not true. But let's see. So if transitive, then what do we need to show? Tell me in words. F is asymptotic to G, and G is asymptotic to H as epsilon to epsilon naught. That should imply that F is asymptotic to H. Okay, so what do we have to show? On the one hand, we know that F over G has limit 1. And we also know that G over H has limit 1, right? So their product will have limit 1. And since we can cancel, then it is transitive. So as long as you do all in that case, you just have to, well, yeah, I think in that case, you should probably assume that every function, none of the functions are zero, except possibly at the point epsilon naught. Okay, so yeah, that's a property called transitiveness or transitivity. So in case you were wondering, so that was a question that was asked from the in-person audience. If F is asymptotic to G and G is asymptotic to H, is F asymptotic to H? And that would give us the property of transitivity. And the answer is yes, because we can simply prove that this guy here, this quotient, this product of quotients has limit 1. It's pretty straightforward to do that. Okay, so we've seen little o, big O, some examples. And now we have this definition of what it means for two functions to be asymptotic to each other. And we saw, thanks to Sam, that it's a so-called equivalence relation, right? It's reflexive, symmetric, and transitive. Obviously, a function is asymptotic to itself. Okay, I skipped that one. And so we've covered this idea of asymptoticness. Now we're going to get into what are called asymptotic expansions. And to study asymptotic expansions, we need to know about asymptotic sequences and series. Before I get into that topic, are there any questions?
And on the other hand, big O and small O are not equivalence related.
I don't think they are. I don't think they are.
Yeah, big O is not symmetric.
Right. It's not going to be symmetric. So the question was, is big O-ness and little O-ness, is that an equivalence relation? Do they have the properties of symmetry, reflexivity, and transitivity? And I don't think so. Okay.
And small should not be reflexive.
Definitely. Well, let's see.
More than a scale.
It's definitely not symmetric. Right.
I think it's
because so an exponential, so we said, you know, if a function is transcendentally small, then it's little o of, so if a function is transcendentally small, then it's little o of epsilon to any power as epsilon goes to 0. So will epsilon r be little o of that function? No, you can't you can't reverse that, because you will get you get the 0 on the bottom instead of the top, so that will go to infinity, that limit. So it's not, this is not true. And big O, I'd have to think about that one. Or did we already disqualify that one?
No, sir.
Okay, I'll take your word for it. In any case, let us move on to asymptotic sequences and series. We need to know what an asymptotic sequence is first. And as with all things asymptotic, you need to know where you're going first. Things are asymptotic, or, you know, all these definitions that we have so far are what are called asymptotic definitions or relations. they all involve limits. They all involve some parameter going to some value. Could be a parameter getting large or a parameter converging to a finite number, but you always have to know where you're going, that or the neighborhood in which you're working. So we say that this sequence phi k equals 0 to infinity is an asymptotic sequence if, first of all, each phi k is a continuous function from I delta epsilon naught into c. So you have to have a set of continuous functions first. Oh, here's my notation for this thing called n0. These are the counting numbers plus 0. Strictly speaking, you don't count with 0. Some people do. They're called computer scientists, right? But everybody else starts with 1. But that's why this set starts with 1. They're the counting numbers, 1, 2, 3. And if you want to add 0, which we often do when we want to make sequences, we're gonna call that n0. So that could be the computer scientist's counting number set. Okay, this sequence is called an asymptotic sequence as epsilon goes to epsilon naught, if and only if phi k plus 1 epsilon is little o of phi k epsilon as epsilon goes to epsilon naught. So let me give you a couple of examples and you'll realize that asymptotic sequences are things you've seen before and could only be this. So here's the first common example. Remember, you have to understand the neighborhood in which you're working. So the neighborhood in which we're working in this first example, let's use the neighborhood of 0. So epsilon is getting small towards 0. Then we're going to use, or commonly use, the asymptotic sequence phi k is equal to epsilon to the k power. Okay, so now what we have to show then is that epsilon to the k plus 1 equals little o of epsilon to the k. So I always like to just write this stuff out, see if I can understand what the heck's going on, as epsilon goes to 0. All right. So what do I have to show in order to prove this? Let's use the simplified thing. Limit as epsilon goes to 0 of what goes on top for the little o-ness. Epsilon k. And what goes, or k plus 1, what goes on the bottom? Epsilon k. So that's limit epsilon goes to 0 of epsilon. And that's 0. So that's good. That's cleared up. So this object forms a asymptotic sequence. So this sequence is an asymptotic sequence. What about this? So what is the neighborhood we're working in here? Infinity, large. And I'm claiming that phi k equal to 1 over lambda k for every k in the counting numbers n0 forms an asymptotic sequence. So what do we have to show in that case? We have to show limit, things are getting large. We have to put the larger index sequence or element of the sequence on the top. So that's 1 over, or lambda to the k plus 1 with a minus sign, right? And on the bottom, we have lambda to the minus k. All right, so what do we have then? This is lambda k over lambda k plus 1, which is just going to be limit of 1 over lambda. Lambda's getting large, so that's going to 0. So generically, in every instance, we have this holds. Now, I didn't define this for things getting large. but I'm going to stop wasting your time and giving you parity of definitions every time. I'm going to start avoiding two cases. Number one is the one going to infinity, and the other one is definitions involving sequences, because definitions involving sequences are also going to be treated like the infinity case. There's not really going to be any separation or need to do that as a separate definition. It gets a little bit labor intensive and mind numbing after a while, so we just drop those definitions. So even though I didn't define this asymptotic sequences for lambda in a neighborhood of infinity, you guys can understand how to get there. I thought actually I was going to flip the page and there it would be. At some point I stopped doing that, but I guess I'm not there yet. Or I guess maybe we are there. We are there now. Now that we have asymptotic sequences out of the way, we can define asymptotic series. There's a finite version and an infinite version. We're mainly going to be interested in the infinite version, so I'll skip the finite version. So the first thing you need to do is suppose that you have an asymptotic sequence in, let's use a neighborhood of epsilon naught. Okay, then we say that this object here is an asymptotic series approximation of f as epsilon goes to epsilon naught, and we write f is twiddle that series. Okay, so this is an asymptotic approximation, infinite asymptotic series approximation of f as epsilon goes to epsilon naught, and we're going to write f is asymptotic to that approximation, that series, as epsilon goes to epsilon naught, if and only if. Okay, so now comes the punchline. I'm defining things after the if and only if. This is new stuff that I'm defining, new words, symbols, and the after part has to be the new things, okay, giving the actual definition. And that's going to mean that f minus the sequence of partial sums, or the partial sum for this series up to and including the nth term, has to be little o of 5m as epsilon goes to epsilon naught. That's what it means. Now, the remarkable thing, I think I forgot to make this remark in the lecture notes in the book. This series does not have to converge for this to be true. Okay, the series does not have to converge for this fact to be true. So we can have f being asymptotic to a certain sequence, but the sequence over here doesn't have to converge in any sense. Okay, doesn't have to converge pointwise or absolutely or anything like that. Okay, so the most common example that we're gonna, so we'll do some examples. Actually, we've already done an example which works for this. Namely the integral that we computed in way back in chapter 1 as an example. So we've already seen applications of this, but we didn't know that that was called an asymptotic series expansion. Now we do. The most common examples that we're going to encounter are going to be asymptotic series approximations like this, where epsilon is going to some finite number. We'll also encounter the infinite case as well. And usually epsilon naught is going to be 0, so we can just throw this part away. So we'll just get a power series in epsilon. Simple power series in epsilon. That's the thing we're going to be working with, producing, and we're going to get excited about that. Okay. Any questions? And online, you can also shoot a question whenever you have it. Now, we'll also encounter examples where instead of using this asymptotic sequence, or sorry, this asymptotic sequence here, we can tweak it slightly. And we could have that asymptotic sequence where our power, the base is the same, but the power is are some alpha times k. So for example, a common one is going to be whenever alpha is equal to a half or alpha is equal to a third. So that's we sometimes call that a power series, and half integer multiples or powers of epsilon whenever we're working with alpha equals a half or 1/3, as the case may be. So this guy is called a generalized asymptotic power series, and then this guy, of course, is our standard asymptotic power series. And of course, we'll be interested in the case where you'll be using the asymptotic sequence 1 over lambda to the k, and so you could just take this guy and sub it in here. And so that's an asymptotic power series as well, but it's an asymptotic power series whenever lambda is going to infinity. Okay. So if you've taken complex analysis before, you've seen power series like that. They're called Laurent series. Okay. Now, if you have an asymptotic expansion, even if that series doesn't converge and it might not play nice, at least we can say that if you have an asymptotic expansion given a certain asymptotic sequence, these are also called gauge functions. There's another term for them as well. Gauge functions and maybe well-ordered sequence, an ordered sequence. And you can see the ordered, that makes sense from the fact that, you know, you have this sort of stacking of little o-ness. In any case, so given an asymptotic sequence, if I have an asymptotic series expansion with given coefficients, then those coefficients have to be unique. They're only they can only be one thing. Okay, so if I have an asymptotic power series expansion of f in this sequence, this is what I'll call this a power series too, even though these aren't specifically powers. Then the first coefficient, the leading order or the zero order, is given as the limit of f over phi naught as epsilon goes to epsilon naught. And subsequent coefficients are given as f minus the partial sum up to order m minus 1, okay, in the asymptotic approximation, divided by, or the limit of this quotient where this is the numerator and phi m is the denominator. Limit as epsilon goes to epsilon naught. So what this is saying is, given some asymptotic sequence, these coefficients are uniquely determined. And you can, and if somebody gives you an asymptotic sequence and the coefficients are somehow obscured, you can always compute them term by term.
I think there's a typo.
Okay,
Uh,
there's almost assuredly, sir, a typo.
the line above equation 12, f x epsilon is tilde. Should it be phi k epsilon?
Yeah, missing a k there,
And
right?
also, I think the last page was the definition of asymptotic theory. Yeah, the finite one you miss a case.
So here's the one on the finite.
You miss no.
Oh, he down. Okay, I see it. I see it. Any other missing guys? Okay. Typos are an everywhere dense set. So they just won't leave you alone. But I do a lot of copy pasting, so typos do tend to proliferate. Once they're nucleated, then they continue to grow by copying. Ah, yep. Okay. So let's start out by assuming that F is asymptotic to this series as epsilon goes to epsilon naught. Then by definition, the sequence, or sorry, the partial sum up to order m has to be little o of phi m for every m. But what does it mean to be little o of phi m? It means that when I divide this difference by phi m, then I'm going to, the limit is 0 as epsilon approaches epsilon naught. Okay, now I can pull off one term from this sum, and that highest order term of order m appears here. I can then form I can make this quotient into two quotients, right? The difference of two quotients by separating out that term from that term. Okay. Of course, when I divide this by this, the only thing I get is AM because they're evaluated at exactly the same points of epsilon. Okay. And so I just get AM with a minus sign so I can move it to the other side. That's independent of epsilon completely, so it can come out of the limit. And so that means that my limit has to be, of this function, has to be equal to AM of x. So that gives me the nth term where m is greater than, so this one works for m greater than or equal to 1. And the only one I'd be missing is the first one. It has a slightly different formula, but I can just take the definition of asymptotic in the first case and get that one. Okay. So whenever you pull that guy off, there's nothing left here. Okay. Or you could read it another way. If m minus 1 is already 0, then there's no summation done here. Okay, so that also works. Okay, fix those. Guess that's an easy one to miss. Okay, so standard assumptions, A and G are continuous functions, and we are going to assume, and of course, assume that we have an asymptotic sequence, phi k. Suppose that F has an asymptotic sequence series expansion in the phi k series like this, and G has a series expansion like this. The only difference here is that the coefficients, of course, are generally different for each one. We now know that those coefficients are uniquely determined through those limits we had previously. So once we have an asymptotic expansion, then the only limits you can get are the limit, or the only coefficients you can have are the coefficients you use. If I multiply a C times F, then this is a asymptotic sequence for C times F. This C can easily come in, and you can show that in a couple of different ways. You can start by assuming that this is an asymptotic series expansion for this function. And then you'll see that the constant C has to be there. If I add two functions together, f and g, then their asymptotic series expansions have to add together. And the way you do that is just add the coefficients together. If I multiply two asymptotic sequences together, or I said that wrong. If I multiply two functions together who have asymptotic series approximations, then their series approximations multiply. And we have this product series where CK is just equal to this expansion. And where this comes from is if you just take power series and you multiply them together, you get a similar sort of thing. The nice thing here is that usually when you multiply power series in the traditional sense together, you have to have a lot of assumptions in order to be able to do it. Like, for example, you have to be able to assume that the series are absolutely convergent, for example. Yeah, question online?
You're missing the K again on the phi.
Okay, thanks. I'm missing a K again. Oh man. I was just copy crazy there. Thank you.
For every missing K, you need to buy one cheeseburger for everyone.
How about for myself? I'm the only one I'm really hurting, right? With this is a deal. Okay. Does that make sense? Now, how would you prove these things? So there are a few different ways. You can go back to the original definition. You could go to the fact that if I have a power series or an asymptotic series expansion, then the coefficients can only be thus. And so then you can show that the coefficients are exactly what they are. I think in this case, probably the definition is the easiest way to do it. Again, the nice thing is with this result is I don't have to worry about any complicated assumptions in order to get this result. Can somebody do a quick Wikipedia? What is the assumptions to multiply power series together? Or maybe you remember. Do they have to be both absolutely convergent for that to happen in a region? We'll get back to it when you find it. But anyway,
Interchanging is if you want to interchange two different summations, you need to satisfy Perturbation, which is the absolute convergence of the double summation.
Yeah, but that's a different thing. This is just plain product of two sequences, not sequences with multiple indices. Fubini is you sum in one direction first, and then you sum over the results.
If both of them finite, then you can do it, because if they're finite, you essentially just doing linearity. You just multiply by constant.
Maybe.
I'm pretty sure at least one of them has to be absolutely convergent, but I can't remember if it's both or not.
Okay. Well, I think correct. Well, let's just say I'm pretty sure that if both are absolutely convergent in the radius of overlapping radius of convergence, then the product series does converge and it has these terms exactly. But I don't have to assume anything about this. It just works. Okay.
I mean,
So
it's the Cauchy product formula. Right?
Is that what it's called?
I think it's
Maybe. Cauchy product formula. That could be. All right. Well, let's move on. So suppose that f is a continuous function that has a power series expansion or an asymptotic, I'm going to say this wrong, asymptotic power series expansion as given here. If phi is some function that is TST as epsilon goes to epsilon naught, then lo and behold, f of epsilon plus phi of epsilon has exactly the same power series expansion as f. In other words, this guy is so tiny that it can't contribute to any of the terms in the power series expansion of the sum. Another way to say that is, no, do it. Okay, I don't have any phi's here to have missing k's, so I'm good. Another way of saying that is phi is equal to the power series expansion k, or sorry, not equal, k equals 0 to infinity. What do you guys think? What do you think? What should it be? 0 times epsilon to the k as epsilon goes to 0. Doesn't make much sense, right? But actually, you have, what's that?
Easy to evaluate.
Well, this doesn't say it's equal to 0. That's where you have to be really careful. In fact, this doesn't say this is approximated by 0 either. It simply says that, if you look at it, it says that phi equals, what would you guess? Little o epsilon k for all k as epsilon goes to epsilon 0. That's what it says. But that just means transcendentally small. Okay. So it doesn't mean it's 0, it just means it's really small. It doesn't get picked up by things, asymptotic computations. That's kind of troubling. Okay. It doesn't get picked up by asymptotic approximations. You have to use a theory of asymptotics called asymptotics to all orders, some new version of asymptotic theory, which can pick up these terms in a non-trivial way. Traditional asymptotic analysis, due to people like Poincaré and those who at the turn of the previous century started figuring these things out. So that asymptotic theory doesn't pick these things up. Okay, it's kind of silent on those. Okay, so again, if you add a transcendentally small term to a function, then it has the same asymptotic series approximation as the original function. So that's kind of cool. Yeah, and so I guess, you know, that is the style of proof. You just show that this has to have the asymptotic expansion in this in this power series, where every coefficient is just equal to 0. But again, that doesn't mean it's 0. Okay, it means what the symbols mean. Okay, guys, people, it means what the symbols mean. Certainly doesn't mean it's 0. Okay, so we got through it, right? So we got through just the notation portion, the basic examples. Now we want to go back and tidy up a couple of the problems that we introduced in chapter 1. So let's think about the problems that we introduced. There was the problem that we started with, that was Stirling's approximation. We're going to tidy that up, put it into the notation that we've just, into the terminology that we've just developed. Then there was the asymptotic expansion of an integral with a large parameter. We didn't know it was an asymptotic series approximation or a series expansion previously, but that's what we're going to establish now. And then there were the algebraic problems, the singular and regular perturbation algebraic problems. And Then we started into ODE problems, and there was a ODE problems of regular perturbation type and singular perturbation type. The singular perturbation problems involving differential equations, that's going to require much more machinery, but we can start saying some things about them. And I'll fill in some more details about those sort of problems in this section. Well, actually in the next section, in the second slide deck. So let's first attack those two problems that I mentioned first, the Stirling's approximation problem and the asymptotic expansion of the integral with a large parameter. So now we can sew this guy up pretty cleanly and say that the thing that we showed initially in chapter 1 involving an approximation for the log of n factorial, well, what we really showed was that the log of n factorial is asymptotic to n log n minus n plus 1. Or in other words, this is an asymptotic approximation of this function. And of course, we can switch them around, right? Typically, the way this is used is this is the thing that you want to approximate, or the thing that's maybe new and confusing or hard and we don't have much familiarity with, relating it to the thing on the right-hand side, which is the approximation, which appears with terms that we're familiar with and that are easier to understand and define. Okay, so we want to prove this asymptotic approximation in 14. How do we do that? Let's define, as we did before, Ln. This is a sequence. Now, again, we're proving things with sequences. We never really had an official definition with sequences, but we know how that would work, how that would translate. So we define this, and we define this thing we called I. I is the integral from 1 to n of log x dx. And log x has an antiderivative. It's x log x minus x. And if I take the antiderivative, use the fundamental theorem of calculus, right? And evaluate at the endpoints of the antiderivative, I just get n log n minus n plus 1. That's because when I evaluate at point x, log of x is, sorry, the point x equals 1, log of x equals 1 is just 0. And so I just get a minus 1, where that's coming from. So what I really want to show is that Ln is asymptotic to In. Okay, so that's Ln here, In there, as n goes to infinity. And this is true if and only if the difference, okay, divided by In goes to 0 as n goes to infinity. That's what it would mean to be an asymptotic approximation. And notice that that also means that this quotient, if I would take that by itself, has to have the limit 1. So we showed in chapter 1 using that Riemann sum argument. Actually, it was more or less a proof by picture that you can just copy over. We showed that this quotient is positive and bounded above by log n over I of n. But L'Hopital's rule, you can show, or via L'Hopital's rule, this is just going to be infinity over infinity. So you have to take derivatives to evaluate the limit. And if you do that once or twice, I believe, then you can show that that quotient is tending towards 0 as n goes to infinity. So this is going to 0. So by the squeeze theorem, this is getting small, right? This is, or the Mack-Truck theorem, if you like. This is squishing this guy down to 0. So that's it. That's all we had to show. And that puts everything in the language of what we already know, okay, or what we just learned from chapter 2. And 5 minutes, so I'm going to get started with this next example, but I don't think I'll get through it all the way. So this will complete once we do get through this example, this will complete the slide deck or the first slide deck for chapter 2. And there's also a second one, which you can download from Canvas. And I've also put them in GitHub. So has anyone tracked down the GitHub repository to search for? Okay, so those, I can't remember if I have the second slide deck updated in the GitHub. Do I?
Yeah, but mine's uploaded for some reason, but
Computer's broke.
most like 70% of it, and it's uploading.
Okay.
We're gonna talk about stealing.
Yeah. I will give the slides away for free, but whether I give the lecture note, whether I put the lecture notes in the wild, I don't know. So I'll think about that. And I definitely won't ever give up the LaTeX code. All right. So what we want to show, so this is the integral that we considered way back in chapter 1. It's been a few weeks now. We're interested in this integral as lambda gets positive. Back then we called it x, as x gets large. And I like lambda getting large. So what happens as lambda gets large? Well, what we can prove is that I of lambda is or has the asymptotic series approximation given here, or I of lambda is asymptotic to this. So this is an asymptotic series representation, and so we know how to compute the terms of that if we wanted to compute the terms. We're going to use a slightly different technique to prove that this approximation holds. All right, so let's examine this. This power series, asymptotic power series, in the sequence. The asymptotic sequence in this case is going to be for the kth order is going to be 1 over lambda to the k plus 1. So that's the asymptotic sequence that we're going to be using. It's the same as the asymptotic sequence that we've introduced earlier, except we're shifting the indices by 1, right? So notice that whenever I'm summing from k equals 0 to infinity, my first power here is going to be the first power, okay? K plus 1, so 0 plus 1, the first power is, instead of being 0, it's just going to be 1 over lambda to the first power. So here are the terms of the sequence. AK is just this, and so it's this here. And then my asymptotic sequence is 1 over lambda to the k plus 1. So we just identified what those objects are in my asymptotic approximation. Notice that this series we said for finite values of lambda does not converge. We've already established that. It's not a convergent sequence or a series, but it is an asymptotic series, okay? So we first have to show that we have an asymptotic sequence, and I'm going to skip that part because that's fairly straightforward. Basically, you just showing that phi k plus 1 divided by phi k converges to 0 as lambda goes to lambda k. And that's a fairly simple computation because it just involves quotient lambda k plus 1 over lambda k plus 2, which is 1 over lambda k. And that clearly goes to 0 as lambda is going to infinity. Now, in our construction in chapter 1, we showed the following. We showed that I of lambda, that's the integral that we want to characterize. We showed that it's exactly equal to this series, this finite series, plus this remainder. And it's not just any old remainder, it's a remainder that we can completely characterize. Okay? So if we want to show that this is approximated by an asymptotic series involving this, then we have to do something with the remainder. So this is an asymptotic approximation of that, or sorry, this series is an asymptotic approximation of I. If and only if I lambda minus this partial sum up to order m minus 1 is little o of phi of m minus 1. Okay, so the goal is then to show that this holds. But we have a characterization of this error, namely, this remainder or error is just given by this integral. So what we have to show then is that this remainder is order phi m minus 1, where phi m is just 1 over lambda m. And we're in negative time here, but this is the last slide, so forgive me. All right, so we know that this is true, which is what we wanted to show, if and only if, well, what we have to do is divide both sides by that guy, or divide this by that. If you do that, we have to show that that limit is 0. Well, that limit is just lambda to the m power times that integral remainder. Okay, the integral defining the remainder. So lambda to the m power has to, when we multiply by the integral remainder, has to go to 0 as lambda goes to infinity. We already showed in chapter 1 that we have this estimate for that remainder. So that means that this guy is at most m factorial over lambda to the m minus 1 power. But for each fixed m, as lambda goes to infinity, we're looking at something like 1 over lambda. So that is clearly going to go to 0. And that means that the result we wanted to prove is true. So again, this is kind of semantics. The series that we have is not a convergent series, but that's okay because we're defining something in terms of essentially the terms of that asymptotic series expansion. We're not saying anything about whether or not the series converges or not. We're just saying, you know, whenever we're using this symbol, it means something a bit different. Okay. Okay. So thank you for giving me that extra minute, 2 minutes. If you have any question, feel free to shoot me an email or stop by afterwards, and I'll be glad to help you out. Otherwise, I'll see you on Tuesday. Have a good day.